if you do nothing twice, so this one, of course you get nothing. Right? Now, if you do operation R followed by nothing, well, of course you get R. If you do S followed by nothing, of course you get S, and so on. So this here, there's a column that's the same as this set. And again here. Okay? So it looks as though this binary operation table has the same kind of phenomenon as that and that. Right? So we're getting to be a bit suspicious that these kinds of sets have a kind of unit type element. Right? We're getting suspicious that that's true. Now, it would be, it'd be. Now, what about associativity? If you take any three of these and you do the associativity test, is this true for all possible A, B, C, any three elements of your set? Like I say, it's tedious, but you can test it and you'll find that it is associative. Okay. Now, it's also closed because look, if you actually bother creating the whole table, you will see that all of these, in every case, there's just one and only one example, and each result, for each binary operation, each result belongs to the set, so it's closed. So now this is also closed. That's closed. So we're starting to collect a list of properties that these kinds of binary operation tables have, or put another way, that the set has with its binary operator. So thinking of like two things: the set and its little circle. In other words, its binary operation. Okay? So closure, closed. That's one property both of these have. We seem to have some kind of unit element, the has no effect type element, and associative, and there's one other. It's a bit more subtle. I'll throw it at you a little bit, save a bit of time. It's called, each element has an inverse. So if you have element A, so any element belonging to your set, there's another element that you write this way, such that A inverse is the same, A inverse A is equal to the unit element. That's not so obvious. You'd have to sort of think about quite a bit, but this is true of this and this as well. Okay? Well, and it's true for every element of the group. So every element. So for all A belonging to your set, there is an inverse element. So usually another element also belonging to the set, such that this is true. Such that this. Okay? Well, now we put those four properties together, and so these four very general abstract properties that these kinds of tables, or these sets with binary operators have. And we define those kinds of sets and operators. So we're talking about a set and an operator, right? It's sort of a duo. You need to talk about both. So we can now define a particular kind of set with a binary operator that satisfies four properties. So if you were trying to prove that a particular set is in fact a group, now we're getting to the nitty-gritty. So the definition of a group is a set with its binary operator that satisfies these four properties. One, it's closed. Okay, we'll talk about closure in another lecture on binary operators. So it's closed, right? So all of these entries here in the table belong to the set, and similarly here belong to the set. Okay, so it's closed. It's associative. So this is true. This is true. Right? So for any triple, any random three elements of your set, you get this. So the order of bracketing doesn't matter. It doesn't matter whether you do that first or that first. The result will end up the same. So the second property that a group has, a group is a special kind of set, is that it's associative. Okay, so you have this, and that there's the third one is that there's a unit element. There's some element of or from the set, so that well here, where is it? If I define it, I'll put it here. Yeah, down here. Is the definition. So there's a unit. It's one particular element from your set, and if you perform a binary operation with that unit on any other element, you'll get that other element, right? So in other words, EA is the same as AE. So you can put the E either to the left or to the right of the other element, and you'll still get the other element. Okay? In fact, it's sort of like if you think of these as numbers and the binary operation as multiply, then in a sense the E acts like a 1. That's how it got the name unit, right? By analogy. It's just, it's not strict. It's just analogy. It's just a label, right? We call mathematicians call that particular element the unit element. And this fourth property, which is a bit more subtle, but every member of the set, there's usually another, it could be the same, but usually another element, so that when you binary operate with those two, the element and its inverse, the result, it doesn't matter which way it is, it's like inverse first or second, the result is the same. The result is that it's the unit. Okay? Alright. So if you're given a set and its binary operator, how would you go about testing whether that pair, that duo, that S, the set and its binary operation, so S little circle, if you like, how do you go about testing whether that duo, that pair, is a group? Well, you have to test for all four of these properties. Okay? You have to test for closure, for associativity. That's the tedious one because there's so many possibilities. The combinatorics are pretty bad once your size of your group becomes large. You have to show that there is a unit element. That one of those elements of the set acts like a unit. In other words, so this is true. Okay, and for each element of your set, there's usually another. It could be the same, but usually another element, such that this is true. Right. So you'd have to prove that. Now, so proving that something is a group can be a bit tedious because you have to go through all those four properties, right? Closure, associativity, the unit, and the inverses. Okay? That's sort of it in a summary form. Now, to prove that something is not a group, like if you're given a set and a binary operation, to prove that duo, that pair, is not a group, all you have to do is just show that one of these is false, right? Like, and you don't even have to show a complete one of these four is false. Just one part of one of them. If that's false, then the whole thing is false. The whole thing is not a group. Okay, so it's generally saying it's much easier to prove that something is not a group than it is to prove that something is a group.